So we're considering a plate whose temperature is held constant at 120 degrees Celsius, and we're given the dimensions and air flows steadily over the flat plate, and we want to find the rate of heat transfer from the plate if the flow is parallel, like in drawing A, to the 8 meter long side, and if it's parallel to the 2.5 meter long side. And these are our assumptions. We need to assume the constant surface temperature, steady flow, flat plate, constant thermal properties, and air is an ideal gas. So the first step in all of these types of problems is always find your T-film, or if it's a pipe problem, find T-bulk. So we're doing the ambient temperature plus the surface temperature divided by 2. Then we look at table A22 at the T-film temperature, and also in the assumptions, if they don't tell you the ambient pressure is 1 atm, then you need to assume that. And then from the table, really all you need is the K, V, and PR values. You don't need thermal diffusivity if you just pull PR directly. And so the next step in this problem is to find the Reynolds number. But let's just define LC for part A, and it's the length parallel to the flow in these forced convection problems. Yeah, so now we want to find the Reynolds number at the edge of the plate because we're trying to find the temperature at the edge of the plate, I believe. And so we need to compare that with the critical Reynolds number, which is 5 times 10 to the 5th for a flat plate. And since it's greater than that, then it's laminar and turbulent. But we need to confirm that it's not just turbulent by finding what X critical is by plugging in RE critical and then taking the full length minus X critical for the length that is turbulent and finding that it's 79% turbulent flow. So we need to use the Nusselt number equation that is correlating to both laminar and turbulent flow. And so plugging in the Reynolds number at the end of the plate, we get this value, and then we rearrange the Nusselt number equation for the heat transfer coefficient H and find that it's equal to 12.385. Then we can use H in Newton's law of cooling to find the rate of heat transfer when the flow is parallel to the 8 meter long side. Now we're going to find when the flow is parallel to the 2.5 meter long side. So we need to recalculate the Reynolds number at 2.5 meters. And like I said before, we need to compare that to the critical Reynolds number to see what type of flow it is, and it's laminar and turbulent, and we confirm, yes, it's only 50% turbulent, so we need to use the same equation for Nusselt number, plugging in the Reynolds number that we had and the PR value, and we get that the Nusselt number is 883, and what I said before about calculating the temperature at the edge of at the end of the plate, that is something that you could find, but for this problem specifically, we're only finding the heat, the rate of heat transfer using the Nusselt number, rearranging for H, and then plugging that into Newton's law of cooling. Okay, now problem 2, consider air at 25 degrees Celsius. It's flowing parallel over a smooth flat plate with uniform heat flux. So before we had uniform surface temperature, now we have uniform heat flux. So now our equations for Nusselt number will change. It's still forced convection though, so we need to remember that. And we want to calculate the local heat transfer coefficient at the trailing edge of the plate and the temperature at the trailing edge of the plate. But since they don't tell us the surface temperature, we need to make a guess for that value, and then confirm that that guess is valid by plugging in 300 watts per meter squared. And I'll go through that in a moment. So it's important to know where the velocity is coming from, because that determines what length you plug into the Reynolds number. So if the velocity is coming in parallel to W, then you would want to plug in the width W into the Reynolds number equation. But it's parallel to L, so we want to plug in L into the Reynolds number equation. So these are our assumptions, and we need a guess for the surface temperature in order to calculate the T-film value, because we need T-film to find our thermal physical properties, alpha VK, because we need V in order to find the Reynolds number, so we need that value. So we first find T-film with the ambient temperature of 25 and our guess, and we need to assume that the ambient pressure is 1 atm, because otherwise we can't use table A22. And we only need thermal conductivity, PR, and V for these types of problems. So we now have V, so we can find the Reynolds number at the edge of the plate, which is 1.5, because the length is 1.5. And we know that the Reynolds number at the edge of the plate is less than the critical Reynolds number, so we only have laminar flow. So we pull the Nusselt number correlation equation that is only for Reynolds number, or for laminar flow, and we get 142.4 for the Nusselt number at the edge of the plate. Then we find the heat transfer coefficient at the edge of the plate using the length that is parallel to the flow, which is 1.5. And then we get, then we use Newton's law of cooling, plugging in that H value that we just got, and we use the value of the heat flux that they gave us to check our surface temperature. And we see that the surface temperature, when we resolve for the surface temperature, it's way lower than what we guessed. So our initial guess was way too high. 124 is not approximately equal to 105, which was our initial guess. So a good strategy for making a much better guess, and if you use this strategy, you only have to guess twice. You just set your next guess equal to what the surface temperature is when you solve it with the known heat flux. So 125 was about what we got. So 125, and then we plug that in, and we get T-film is 75. And then we recalculate the Reynolds number at the edge of the plate using the new value at this different T-film for V, which is 2.046 times 10 to the negative 5. And then we plug that into the same equation for Nusselt number. We get a different Nusselt number, and we plug in Nusselt number into the heat transfer coefficient equation using the same length. The only difference now is like the initial guess for the surface temperature. So now we resolve for the surface temperature to confirm using the known heat flux. We get that it's approximately equal to 125. 125.64 is very good solution. So we know that the heat transfer coefficient using this initial guess of 125 is accurate. So now we know the surface temperature and we know heat transfer coefficient, which were the two things they wanted us to find. So again, just make an initial guess about 100 or 200 off. Usually just make a guess that's 100 more than the ambient temperature. Solve for heat transfer coefficient. Use the known heat flux to resolve for the surface temperature. And then make sure that they're about equal to your guess. And so this is the code in MATLAB so that we can plot the surface temperature and the ambient temperature span-wise along the flat plate. And we can see that surface temperature is about equal to the ambient temperature at the edge of the flat plate, and it's not exactly equal because I didn't plot it, because if you divide by 0 then you get an error, but that's why it stopped a little early. But surface temperature does equal ambient temperature at the edge of the plate. So problem number 3, consider air flowing parallel over the upper surface of a flat plate. The length of the plate is given, and the first half of the plate has constant surface temperature, and the second half of the plate has constant uniform heat flux. And this is a forced convection problem because we have air flowing. And so we have 2 separate Nusselt number equations for when you have this constant surface temperature and when you have uniform heat flux. So we need to separate those 2 sections in our brains, and then really the gist of this problem is not overcomplicating it. So we've got this sketch here with the surface temperature being constant in the first 2 meters and the heat flux being constant in the second 2 meters, and we've got our assumptions: steady flow, flat plate, constant thermal properties, air is an ideal gas, and the ambient pressure is 1 atm. You need that to use table 822. So first we're trying to find heat transfer coefficient at 1 meter. So you just treat this as a normal heat, like a normal problem. We're trying to find the heat transfer coefficient for surface temperature when it's constant. So you find the T-film, then you use T-film to find your thermophysical properties, and then you use your thermophysical properties to find RE at that specific location, so at 1 meter. So we plug in 1 for X, and we get this local Reynolds number, and we get that the Reynolds number at X, not at L, it should be X right there, is less than RE critical, so it's only laminar, so that determines what Nusselt number equation we use. So then we plug in everything we know, and then we have NU. We plug in NU to find the heat transfer coefficient. Plugging in L is 1, because length is the distance parallel to the flow where you're trying to find that value. So now we want to find heat transfer coefficient at X equals 3. So what you would probably initially intuitively do is like subtract off the section that is constant surface temperature, but just treat this problem as your whole flat plate has uniform constant heat flux up until X equals 3. So for this problem, we don't know the surface temperature, so we're going to make a guess, because for uniform heat flux, surface temperature is not constant, so you want to make it a guess, and they don't tell you what it is. So then you find T-film, you use T-film to find your thermophysical properties, then you use your thermophysical property V to find the Reynolds number at 3. And then since the Reynolds number is less than the critical Reynolds number, it is only laminar flow. And then you use that to find the Nusselt number. Then you use the Nusselt number to find the heat transfer coefficient, and again, you use L as 3. Just assuming the whole plate has uniform heat flux, even though half the plate doesn't. And you rearrange the equation for Newton's law of cooling for the surface temperature, and you find that it doesn't really equal what you guessed, which was 90. So you need to set your better guess equal to what you did get, which was about 50. So T surface is 50. And that was the same as before, so you have the same V value, the same PR, the same thermal conductivity K. So it makes the problem a lot simpler. You find Nusselt number using the laminar equation. And because in our first guess we did find that it is only laminar up until x equals 3, so that's all that matters. And then we find the heat transfer coefficient, rearrange for TS, and find that it does equal 50.14, which is about equal to our T guess of 50. So this heat transfer coefficient that we found in the previous line is accurate, and that's the heat transfer coefficient at x equals 3.